Hello, my name is Miłosz from Poznań Supercomputing and Networking Center. I will give a presentation about energy efficiency and performance modeling of Stencil applications on Manycore and GPU computing resources. The plan of my presentation is as follows. At first I will give the motivations, then I will briefly describe the Stencil computations. I will tell about the DC worm simulator. I will formulate the problems. I will describe the extensions that we implemented in DC worm simulator, and I will conclude my presentation. High-performance computing systems have to deal with restricted power limits and associated energy consumption costs. Additionally, we have been observing the increasing complexity of parallel and heterogeneous HPC resources over the last decade, and this trend will continue. So at the hardware perspective, there are many design efforts to improve the energy efficiency. One of the most critical application areas for many operational high-performance computing systems worldwide is a numerical weather prediction. Such complex predictions and corresponding computing models have to solve a large number of partial differential equations using Stencil computations on structured grid with tight production schedules. Preparing NWP services for the next generation of supercomputers is still a big challenge, as both HPC software and hardware have been changing a lot over the last 2 decades. A full port of legacy NWP models is naturally feasible, but it requires advanced technical expertise combined with time-consuming and costly experiments on real HPC hardware. From the software development and performance perspective, a Stencil kernel within an NWP application is often the most demanding computing part, and consequently it has also a significant impact on the energy consumption of underlying HPC system. What is even more important, a Stencil pattern represents a variety of other practical HPC simulations ranging from geophysics to medical science. As we can see, Stencil computation is defined on a multidimensional structural grid where each point on the grid is updated with a strict pattern. The pattern defines which neighboring points are used during a Stencil computation. A single update of the whole grid is called a time step. The challenges with complex software and hardware have already encouraged many researchers to work on various performance modeling tools to be able to estimate and optimize the overall performance of both HPC software and the resources. In Poznań Supercomputing and Networking Center, we developed the data center workflow and resource management simulator called DC worms. DC worms enables the flexible modeling and simulation of both heterogeneous and hierarchical computing infrastructures to estimate their performance, energy consumption, and energy efficiency metrics for diverse workloads, as well as resource management and scheduling policies. The overall architecture of DC worm simulation tool is presented. Technically speaking, DC worms is an advanced, event-driven simulation tool written in Java based on many useful libraries. Generally, input data for DC worms consists of workflow and resource descriptions. These inputs can be read from real system, log, or traces, or generated using the workload generator tool that allows creating synthetic workloads. Nevertheless, the key components which add a lot of flexibility to DC worms are plugins. In nutshell, plugins allows the user to configure their simulation environment, taking into account specific research needs by modeling joint performance, energy estimation, and also implementation of resource management scheduling policies. Simulation experience performed in DC worms required a description of application requirements and characteristics that will be used during jobs and tasks, management, and scheduling processing during the simulation. For the basic workload format, DC worms accept files in well-known standard workload format or grid workload format. In addition, some more detailed specification of job and task can be included in an additional file based on XML-based job schema from the CCGrid. This format description extends the basic one, provides a scheduler inside decimals with more detailed information about certain application profile, task requirements, user preferences, and execution time constraints. To facilitate the process of adapting the traces from real resource management system, DC-Worm supports reading the very those delivered from the commonly used local resource management systems. As modeled applications may vary depending on their nature in terms of their requirements and structures, DC-Worms provides the user with an appropriate flexibility in defining an application models. Considered workflows may have various shapes and levels of complexity that range from multiple independent jobs through large-scale parallel jobs up to complex workflows containing time dependency, preceding constraints between jobs and tasks. Each job may consist one or more tasks, and these can be seen as group of processes. So our problem is, so we use the DC-Worm simulator to simulate dynamic stencil workload execution on heterogeneous computing architectures to predict both the energy usage and the overall performance. So in our case, a stencil-based simulation experiment is defined by a set of n processors and of n independent tasks. Stencil task can be characterized by number of grid cells to process, number of arithmetic operations per grid points, and number of required bytes to update the grid point. Processing Unix is characterized by available cores, available frequencies, a set of states, and a sustained bandwidth to the main memory in bytes per second, and performance in flops. When we have parameters for both the tasks and the processor, we can estimate the execution time. So we have to calculate the overall number of arithmetic operations executed, overall number of bytes transferred. When you have these both parameters, then we can estimate execution time by taking maximum from how much time it takes to do the computation and how much time it takes to send the data. And the energy cost, so in order to calculate the energy cost, we have to estimate another three parameters: energy cost to compute a single flop, energy cost to communicate single byte of data, and the constant power usage. So we can use this equation, and the parameters can be extracted from three different methodologies: source code analysis, hardware performance counters, and compiler instrumentation. The main idea was to present a flexible solution to users with different needs and possibilities. For instance, some users could prefer a static code analysis as a quick method to estimate model parameters without any need to execute an application of physical CPU or GPU resources. However, if they had an access to real computational resources, they could employ additionally more precise methodologies such as hardware performance counter or compiler instrumentation. The source code of this considers you can see this source code of the 7-point stencil applied for the computation on the grid, and we can see that there is one multiplication and 6 additions per each grid point. So the stencil code analysis can be conducted based on the assumption of the efficiency of underlying memory hierarchy. The worst case scenario assumes that none of the data can be cached during the execution of the stencil statement. The best case scenario assumes an infinitely large cache where all data can be cached as an opposite. In a nutshell, there are two types of operations in the reference stencil: a single multiplication and 6 additions. Each word consists of 8 bytes, as the double precision computations are typically employed in the stencil-based applications. For the worst case scenario, we can consider 7 flops as 8 words are loaded and 1 is stored in memory. In cache-coherent processing Unix architectures, for example, Manycore Intel CPUs, each operation in the main memory is followed by the load of the cache line from the cache memory. This operation is a well-known cache coherency policy, and is called write allocate. For the best case scenarios, 7 flops are executed, the one more is loaded, and the one is stored in memory. The write allocate policy can be omitted with the streaming stores. However, the streaming stores are not always appropriate as they omit cache. The source code analysis method allows estimating all the needed parameters to calculate the execution time of Stencil computations without the need to access and execute the code on the processing unit. As shown in the table, the CPU processing unit can achieve up to 5 and 24% of its peak performance for the worst case and best case scenarios. In case of GPU, it's about 1.6% and 6.4%. And for the hardware, we use another methodology to estimate the number of arithmetic operations and the bytes moved by using hardware performance counters. And for this, we use the two compilers, GCC and ICC. What it's worth mentioning is that for the GCC O2 flag, we received 0, and that's it's because this that the AVX instructions are measured. Measured is that there is no hardware performance counters for the other floating operations on the Haswell platform. And we also estimated the number of bytes moves, and in case of GCC it was 640 gigabytes, in case of ECC it was 512 gigabytes. ICC was able to use heuristic and to enable the streaming stores. That's why the value is lower comparing to GCC. And in this table we show the estimated values of energy cost for double precision floating point operations and the transfer of single byte of data in our Stencil code. The floating point operation is about 6 times more expensive on CPU than on GPU, and the cost to transfer a single byte of data is about 5 times larger on CPU comparing to GPU. And to estimate the number of flops for the Intel Manycore CPU, we use the compiler instrumentation approach. The Intel Software Development Emulator tool emulates instructions on Intel 64 instruction set. This tool can generate histograms of instructions executed, their length and category. For example, many scalar and vector instructions can be counted with what is relevant in our case. So table presents the generated histogram for the ICC compiler. So in general, there are 112.5 megaflops executed. And the energy usage of the reference 7-point stencil can be calculated based on both parameters depicted in the previous sections and approximated energy coefficients. The obtained results shows that the energy usage on the GPU is approximately 6 or 7 times lower on GPU than on Manycore CPU. In these modes, we are able to distinguish 3 main factors and corresponding parameters which will impact the overall application's performance P, denoted as a function of SLA, where S is a set of parameters related to hardware states, L is a set of parameters related to the load, and A is a set of application-specific parameters. The task description schema in DC Worms is the second principal object, and this was extended for the Stencil computation needs. The available extensions give users the possibility of providing input parameters necessary to compute source code analysis and comparative parameters derived from application profiling procedures as presented in the slide. As it was introduced and explained in previous slides, all the application-specific parameters for the experiment in DC Worms should be given a pair of a number of arithmetic operations per grid cell, number of bytes per grid point. It is getting a bit more complicated when application profiling data is entered. Then each combination consists of the following parameters: a number of grid cells, a number of time steps, And in the next step, it is possible in DC worms with pair, frequency, and number of allocated cores to characterize the following application parameters: a number of arithmetic operations per grid point, number of bytes per grid points, time to finish all the communication, and computation and communication routines. Each Stencil computation pattern keeps information about the frequency and the number of allocated cores, which DC worms should perform simulations. And we extended DC worms with a new statistical module with the support of an external graph utility, GnuPlot. This extension allows users to receive plotted information about the results of model-based computation compared with given source code analysis and profiling data. In other words, DC worms supports now intuitive visual performance model and resources performance estimates of a given application. Moreover, users are able to compare data from the current simulation with the historical data, setting the appropriate configuration file. Taking into account Stencil computation requirements, users can use this utility to generate charts based on the roofline model depending on input data. Here we show the example Stencil application performance chart generated by DC worms, and it was based on 7-point Stencil. On the x-axis, computational is measured in flops in flops per byte, and on the vertical axis shows the overall resources performance measured in G-flops per second. Horizontally, blue lines presents the maximum achieved performance for the current frequency and the number of allocated cores. Diagonally, purple lines shows the bandwidth, RAM, and cache memory. Here is another example for the GPU. And we also generated another examples, and one of the real NWP dwarfs selected for modeling our test was the spherical harmonics dwarf. This spherical harmonics dwarf is commonly used as a building block in different weather models such as integrated forecast system, IFS. And here is another example for the same dwarf but on different processor, in this case for the Skylake CPU. And to conclude my presentation, we investigated the problem of energy efficiency and performance modeling of Stencil applications using DC worm simulation framework. Presented a set of comprehensive performance studies of the modeled and reusable benchmark for Stencil codes, compared the overall performance achieved during our experiments executed on real heterogeneous hardware setups for Manycore CPUs and GPUs, and modeled simulation in DC worms. Demonstrated that DC worms capable of modeling cache-aware energy rooflines together with new time-to-solution and energy-to-solution parameters. Researchers can discover numerical code limitations concerning existing hardware constraints using DC worms, in particular in many CPUs and GPUs, as there are plugins and templates available for using in new simulation experiments. So thank you.